Hello everyone. Uh, yeah, so far we have seen the notion of groups, and we also have seen certain specific examples which, yeah, which, certain specific examples of groups, and yeah, so there are certain questions that some of you have asked me during the office hours. So in today's lecture, we will try to address some of those questions. Okay. So, so these are the natural follow-ups of the notion of groups, or uh, yeah, the notion of groups, or the proper these are how to say, these are certain follow-up properties of the notion of groups. Okay. So, for instance, if you, I hope you have been through these notes. If you go back to the definition of groups, you will see that there are five conditions. So you will try to focus on the sorry we'll try to focus on the fourth condition and the fifth condition, okay, today. uh, because I was trying to say that there is something called this the identity element. So why is this called the identity? We'll try to show that there cannot be more than one identity element, and here we will show that x is equal to y and so on. Okay. Yeah. Let's see. Okay. So let's begin with an example. Let's consider the set M2R of 2 by 2 matrices with real coefficients. Uh, okay, so the 2 by 2 matrices were ABCD inside R. So the exercise is to show that this forms a group with respect to matrix addition. So uh, yeah, in the previous lecture we have discussed the specific case where we had this group S1, right? Uh, so where we had to verify those five conditions first. Okay, like the fact that S1 is a set, we didn't need to do anything. And the next thing was that this composition law is well defined, so that we checked here. And then the associativity, it was left for you as an exercise. And then we showed the existence of identity, and we showed the existence of inverse. Okay. Yeah. So I'll it will be much better if you do if you verify all the steps on your own. Okay. But I'd like to point out the key steps that we need to go through. Okay. So the first thing is that M2R is a set. We need to just, there is nothing to verify. We need to just make this observation that is a well-defined set, something like that. Okay. And that for the operation or the composition law that we have in mind with respect to that composition law, if you take any two elements from that set and combine using this composition law, that is, you look at A plus B, so whether there is an element inside M2R once again or not. Indeed this is so, because if you take two matrices inside M2R, then their sum is also an element of M2R, right? The third condition is that associativity condition has to hold, which is true for matrices, because matrices with real coefficients, because addition of, so when you add two matrices, their individual entries, they just get added. Okay, we add along their individual entries. So since addition of real numbers is associative, it follows that addition of elements of M to R is also associative. Okay, then one can show that 0 0, this matrix, the zero matrix works as identity. This is straightforward to see. And then for any element inside M2R, there is this inverse, etc. Okay. Yeah. So with all these steps, anyway, so this is not actually hint. This is essentially the key steps. What this actually counts as a true proof, probably. Yeah, but in a true proof, there should not be any bullets. Anyway, so yeah, maybe this with little bit more elaboration tells you that really just one sentence more elaboration tells you that M2R does form a group with respect to matrix addition. Yeah, so you might have already taken a look at the problem set that I have posted. So there's an exercise which asks you to do the same for M and R for the set of all n by n matrices with real coefficients. Okay, so you need to follow exactly. Okay. So you need to follow exactly all the steps The idea is not that just because, I mean, the point is not that I have provided all the steps so you need to follow. The point is that to show that this is a group with respect to matrix addition, so you need to verify the five conditions that is there in the definition of group. Okay, so you can also try to look at this group of two. I mean, okay, this is not yet a group. We do not know. We can try to look at the set of all 2 by 2 matrices with real coefficients and that has non-zero determinants. Okay, so again, there is a similar exercise in the problem set which deals with GLNR. So that deals with that consists of two n by n matrices with real coefficients. By coefficient I mean these entries. Okay, the entries are real and they have non-zero determinants. Okay, so to show that that forms a group with respect to matrix multiplication, we will just try to do it here for n equal to 2. Okay, we will focus only on GL2R. uh, yes, sorry. Yeah, so there are again, as usual, 5 steps to verify. So you need to first see that GL2R is a set, and then if you pick two elements AB from GL2R and combine them using the composition law proposed or given, then the output has to be an element of the same GL2R. So the output is A times B, and you know that product of two matrices, I mean product of two by two matrices is a 2 by 2 matrix, and if those two matrices have got non-zero determinant, then this product also has got non-zero determinant, right? So, I mean, you only need to use the fact that, or not, I mean, this is an element of GL2R since determinant of A dot B is determinant of A times determinant of B, and since both of them are, so we know that this is non-zero, we also know that this is non-zero, so that implies that this determinant of A dot B is also non-zero, right? Okay, great. Yes, so this is a 2 by 2 matrix, right, with real coefficients, and this has, and sorry, and these has got non-zero determinant, so this is an element of GL2R, right? Okay, and the associativity is also, I mean, it's also easy to verify, that I leave for you to do. I mean, you need to write certain, I mean, you need to go through certain steps, and you have to do certain elementary algebra, but nothing beyond that. Okay, so I leave it to you as an exercise. But the point is that this has to be verified. Okay, so I mean, this is not a hint, or maybe, yeah. Okay, so the better word could be just outline. Okay, I'm calling this an outline because there are certain things to verify. Okay, maybe this one is relatively easy, but anyway, uh, oops. So outline of a proof. Okay, great. So, and here you'll see that this works as identity. Yeah, I mean, this is easy to see. And again, for any matrix inside ABCD inside GL2R, you can look at this matrix. That makes sense because AD minus BC is non-zero, and one can check that this equality is hold. So with that, we are done. So here, this has to be verified. Okay. Yeah. Okay. So now let's just try to see certain features of these groups. Okay, so M2R has the nice feature that A plus B is B plus A for all for all AB inside M2R, and this group okay, just let me put it in words, or let me just indicate that this is a shorthand for all. Okay, so this says that A plus B equal to B plus A for all AB inside M2R. So in other words, you just pick two elements A and B from M2R and decompose them. I mean, it doesn't matter, the order is not important. You can I mean, take A first and then B, or you can take B first and then A. You can compose A with B, or you can compose B with A. So the output is going to be the same. Okay, great. So here inside GL2R, the situation is a bit different. Uh, what to write? Maybe let me write it here. So it is not that, it is not true that okay, this is not true that a dot b is b dot a for all a b inside GL2R. This is not true. So what? So what does this mean? Uh, so that is, so what does this mean? Does it mean that a dot b not equal to b dot a for all AB inside GL2R? Okay, so do you see that, I mean, do you see this statement? Okay, or do you agree this statement, I mean agree with this statement? Okay, so if you do not agree, then I will be happy, because this statement is false. Note that it says that, I mean, this statement that a dot b is equal to b dot a for all AB inside GL2R, that is not true. Okay, so under what condition this will not be true? I mean, that this has to fail, right? This equality has to fail for some AB inside GL2R, right? If you say that, I mean, for all, I mean, for every choice you are in a good shape, okay? If you say that for every choice we have an equality, and then you say that this statement is false, that means for some choice you do not have that equality, okay? So please be very careful with this kind of situation. So when I wrote that a dot b is not equal to b dot a for all AB inside GL2R, this is false, okay? I mean, so this does not imply this. So I'm saying that is, so that is, I mean, you can assume that, I mean, that is probably stands for implies. Okay, I mean that is it. I mean the phrase that is bit ambiguous, but with implies you can certainly say that this implication is false. Okay. Anyway, so let me just put it in, highlight it in red. Okay, so this is false. What one can say is that a dot b is not equal to b dot a for some, for some a comma b inside GL2R. Okay, so here is something that can help you in some way. So you are just, I mean, very roughly speaking, okay, you are negating this for all. Okay, so you are taking the, I mean, negation. So if you negate for all, I mean, it gets replaced by for some. Okay, so just to give you a quote unquote real life example, for instance, if I say that, uh, how to say, mm, if I say that I have got maybe more than 90 in all the subjects in my school, I mean, maybe, say maybe in 10th standard, I have, I mean, so suppose I say that I have got more than 90 for all subjects. Okay, so if I say I have got more than 90 for all subjects, and if I say that that is not true, that means I have failed to get at least 90 in at least one subject, right? So, and for some subject my score is less than 90. So for all has to be replaced by for some. What I said is not a proof, this is just an explanation. Okay, anyway, so, and how about this statement? This statement is not, I mean, this statement I haven't established, I just stated that this is not true. Okay, just to compare this with the situation of M2R. Okay, I told you that this is not true, but again, to be able to do math, we need to have a proof. So our task is to show that there are elements AB inside GL2R such that AB is not equal to BA. This is not too difficult to do. You just take two specific choices for A and B. Okay, and I mean, uh, then it may happen that AB is not equal to BA if you have got the right ones. Okay, so to give you two explicit instances, here is mm, to give you two explicit instances, here are certain examples of A and B. Yeah, so here is another task for you, an exercise that I haven't kind of written it down before. The exercise is to show that, oops, exercise is to, okay, so I'll state it later. So the idea, I mean, I was trying to something similar, something similar. So I have to explain what do you mean by something similar. I'll introduce the terminology later on. Something similar happens in GLNR for any n greater equal to 2. Okay, for n equal to 1 you won't have such situation, you won't be in such situation, because GL1R is just a set of all I mean is a group of all non-zero real numbers with I mean under, how to call, under multiplication. Okay, so now we look into, sorry, yeah, so now I look into U2R. So this is a group of all I mean, okay, this is not yet a group, this is just a set of 2 by 2 upper triangular matrices with real coefficients and containing 1 along the diagonal. So U2R is just this. The exercise is to show that U2R forms a group with respect to matrix multiplication. That's an interesting exercise to work on, so please try to write down all the steps. And this is just about 2 by 2 matrices, so things are not at all difficult. Okay, okay, fine. So now we focus on something called Klein 4 group. This is a very important example. Uh, okay, I mean, this is a group consisting of 4 elements. So here we have this set consisting of these matrices having plus minus 1 along the diagonal. We need to verify whether that forms a group under multiplication or not. Anyway, the title of this exercise says that this is Klein 4 group. So you already probably know, or you could guess, that the set consisting of these matrices does form a group under matrix multiplication, and in that case you are right. So you need to just show that this is indeed the case. Okay, anyway, so there is usually some room of confusion when there are several occurrences of the symbol plus minus. So what I mean here is that the set contains these 4 elements. Okay, so the diagonal entries could be one of, I mean, any diagonal entry lies in the set plus minus 1. So there are 4 choices, so you've got 4 matrices there. Okay, and that's why this is called, I mean, 4 group, and this was studied by Klein. So, and that's why this is known as Klein 4 group. Okay, so you know that this is a set, nothing to worry. And then if you pick 2 elements A and B from this set, you need to show that if you compose them using the composition law provided or proposed, you'll end up getting an element inside this group. Okay, so we denote this set by G. So this is clear that G is a set. I'm just highlighting this in order to make sure that we somehow recall all the conditions in the definition of a group. Okay, okay, great. So now the product of any 2 elements of G is an element of G. This is easy to see. Okay, and here note that 2 does not mean 2 distinct. Okay, this is an important thing to verify. And note that for any 3 matrices ABC inside G, for any 3 matrices ABC inside G, we have this condition. Okay, namely this associativity property holds. Okay, because this already holds inside GL2R. So this is a smaller set than GL2R, so this will be automatic. Okay, and now, sorry, you have to look for the existence of identity, which is already there, and now you have to look for the existence of inverse, that again one can check. Okay, because the point is that how to say, I mean, to get the inverse, I mean, you have to look at this denominator. The denominator, I mean, this determinant of these matrices happen to be plus minus 1. Okay, so you are just changing A, B, C, D by certain signs. Okay, although you have got minus sign here, but whatever it is, the entries of this matrix B are A, B, C, D divided by either 1 or minus 1. Okay, so they are no different from ABCD. I mean, they're same as ABCD up to a sign of plus minus 1, right? And now note that so here this how do you call this, off diagonal entries probably. So these entries are 0, so BC is anyway 0. Okay, so BC is 0 for any matrix ABCD inside G. Okay, so if BC is 0, these 2 entries, they vanish. So these 2 entries are also equal to 0, And now these two entries are just equal to a and d, right? They're equal to a and d with I mean up to signs, right? Up to sign of plus or 1 or minus 1. So since AD lie along the diagonal, they are either 1 or minus 1. Okay, each of them are elements of plus minus 1. So if you change their signs, they also remain, I mean, 1 among 1 or minus 1, right? So B has to be an element of G. So this statement, I mean, one has to kind of spend some time to verify that this matrix lies inside G. Okay, anyway, so make sure that you realize the importance of I mean this discussion. Okay, I mean you can also kind of do it by hand. You can look at the inverse of each and every element. That's fine, nothing wrong. But yeah, but this has to be verified. Okay, okay, great then. mm, Now we go back to this fourth and fifth condition in the definition of group. Okay, so this first proposition says that if you start with a group, then it contains exactly one identity element. Okay, so I mean, this is not too difficult to see, and we'll see it right now. So you pick, for instance, I mean, suppose there are two elements inside G, and suppose both of them are identity elements. Okay, so in other words, so G star E1 is E1 star G is equal to G, and G dot E2, sorry, G dot E2 is same as E2 star G is equal to G. So then you see that E1 star E2 has to be E2 because E1 is E1 is an identity element, right? So in other words, you are using condition 2 here. Okay, so E1 star G is G. So replacing G by E2, you get this. One can do so because this holds for any G. Okay, so you can substitute any of your favorite group element here. So you have E1 star E2 is equal to E2. On the other hand, here you know that these two are equal, right? So now if you replace G by E1, then you will see that E1 star E2 is equal to E1, right? So E1 star E2 is equal to E1. On the other hand, this is also equal to E2, right? So you see that E1 is equal to E2. Okay. Yeah, so now the time is to focus on the fifth condition, okay, which talks about, I mean, anyway, the inverse. I mean, we'll introduce the terminology in a moment. So there is certain convention that I'd like to introduce. So it makes sense from now on to talk about the identity element, right? I mean, which is already there in the definition, but we need to confirm. I mean, because I mean, we need to confirm that the use of this article the makes sense. Okay. So the identity element of a group G comma star is often denoted by the letter E. This is a standard convention. Okay. But you will also see certain other conventions here. Sometimes it is also denoted by 0 or 1. Okay, so make sense that, I mean, so make sure that I mean at certain points one can indeed use these notations to denote the identity element. Okay, just go back to some of the previous examples, you will see. Okay, okay, great. So now again look at the again we go back to the previous conditions. So there is something that I would like to just point out and highlight. So first of all, in the fourth condition that we have in the definition of group, so I mean there we talk about the identity element. Okay, so that certainly makes sense. Okay, and let's also try to recall the third condition, that that this which is the associativity property. Here there is something that I would like to point out, that this definition or this condition does not require that GHK has to be distinct. Okay, so whenever we talk about, for example, two elements or three elements, we mean that we are just picking three elements in some sense. Okay, I mean we do not specifically impose the condition that those three elements are distinct. Okay, yeah, and so here this article the, so this is meaningful by the above proposition, by proposition 32. Oops, sorry, scroll a bit too much. So this makes sense by proposition 32, and now we are going to work on the fifth condition. Okay, yeah, so you start with a group G comma star and denote its identity element by E. Okay, and suppose we have three elements GXY inside G that satisfy the fifth condition. In other words, this equalities hold, and so then it follows that X is equal to Y. Okay, This is easy to see that x equal to y because x has to be x star e, okay, because e is the identity element and e is same as g star y, right? So which is g star y, and by the associativity property this is same as x star g then composed with y, right? And x star g has to be identity, right? So x star g is identity, so this is identity star y, and by the usual property, this property of identity, you know that e star y has to be same as y, okay? So you already see that x equal to y holds. Moreover, you can assume that there are other elements x prime y prime inside G such that this the fifth condition. You can assume that there are elements x prime y prime inside G which are all for which the fifth condition also holds. By that I mean we have this equality. Okay. Then by the previous step, you know that the previous step tells you that x is equal to y. The previous step tells you that this equality implies x equal to y. Okay, so by applying the previous by applying the first part of this proposition right now, we see that this equality implies this equality implies x prime equal to y prime, right? And the first condition implies that x equal to y, right? And from this we have to see that y prime is equal to x. Okay, you can try to do this computation once again. Y prime is this is something that you can go through and you can verify, uh, but let me just try to give you uh, some some very elementary idea that allows us to somehow bypass all this computation. Of course you have to rely on the first step. There is no escape, so some such argument has to be there at the background, in the background. uh yeah, so let me just write it down. So first part implies that x equal to y, or first part in how to do that. The first part implies that, yeah, this implies that this violet one implies x equal to y. Okay, and so we have that, so it follows that x prime equal to y prime, right? And now yeah, so now you're assuming this, right? Okay, and you have also assumed this, right? mm, then you can write the following. You can, you do know that x star g is equal to e, right? Okay, you also know that g star y prime is also e, right? So g star y prime is also e, right? And then you are done. Then again we apply the first part, which says that any such equality will imply that these two quantities, they have to be the same. So you get that x equal to y prime. So by the first part, x equal to y prime. So earlier you had x equal to y and you had x prime equal to y prime, and now you have seen that x is equal to y prime. So all these four quantities, they are the same. Great. And now we are in a position to talk about the inverse. So if you have a group G, then given an element G inside G, its inverse is denoted by G raised to minus 1. Okay, so now you still do not know what is the inverse, because I have told you its inverse is denoted by G raised to minus 1, and this is defined to be the unique element inside G, such that G inverse star G is G star G inverse is E. In other words, G inverse is this element X, or G inverse is also the element Y, it's also X prime, it's also Y prime. Okay, yeah, so given G, you know that you can find something such that that element star G is E, and G star that element is also E, and you know that that element is unique. So that element is denoted by G raised to minus 1. Okay, the idea is that kind of when you compose, then you add the exponents. Okay, you will get G power 0, and that has to be identity. Okay, this is something that no one can prove. This is a convention. Okay, so let me introduce this convention. So if you pick an integer n, it could be greater or equal to 1, it could be less than or equal to minus 1, or it could be 0. For that, G raised to G raised to n. So okay. Aha. there is nothing wrong, but okay, let me explain you what is written here, but then I will explain the trouble. Okay, so g raised to n for n greater or equal to 1 is defined to be g star g star g taken. Hmm, uh yeah, I mean g star g taken n times. Okay, yeah. So for example, g power 1, by convention it is equal to g power 2 is equal to g star g by convention. And here if n is less than or equal to -1, for example n equal to -2, then you compose g inverse with itself 2 times. Okay, and if n is 0, then g power n is defined to be, okay, so this is a convention. This is something that no one can prove. Okay, in our school days sometime we used to quote unquote prove that 2 power 0 is for 1, but there is just no proof of this equality. Okay, this is the convention. Anyway, uh hmm so the trouble, I mean, this, sorry, all this looks good, and in fact, I mean, this is good, there is nothing to worry, but there is a kind of a minor trouble here. So what happens when n is -1, this exponent is -1, then you are defining g raised to -1. I mean, but here one is to kind of observe first that, or keep in mind that g raised to -1, this notation has already been defined. Okay, so here if you take n to be -1, you are defining g raised to -1, and let's see what do you do. To define g raised to -1, we say that you take g raised to -1 one times and compose with itself. Okay, so you are using g raised to -1 to define g raised to -1. This is certainly not allowed in mathematics, I mean, or nowhere in life. uh, so this is bad. This has to be -2, and yeah, so for an integer n not equal to -1, because yeah, so now this is good. So given a group g, an element, given a group g comma star and an element g inside g, and an integer n other than -1, I mean, our kind of a, I mean, so after defining g raised to -1, our next task is to define g raised to n for any integer n other than -1. So that's what we have defined. So now things make sense. Great. And as you see, certain kind of laws of exponents that we are familiar with since our school days, so they are still valid in the context of groups. Okay, almost by definition and almost by the same principle that we learned in our school days. Okay, but again, this has to be redone. So this is an exercise for you to show that for any two integers m and n inside z, g raised to m star g raised to n is g raised to m plus n, and g raised to m raised to n is g raised to mn, and so on. Okay, okay, great. Now let me introduce certain further notions. So where we deal with something called abelian groups. So a group g comma star is said to be abelian if if g star h is h star g for any gh inside g. Okay, and if a group is not abelian, then it is said to be non-abelian. Okay, so what is an example of an abelian group? You have already seen M2R is an abelian group, GL2R is a non-abelian group, and while discussing this problem on GL2R, I said that something similar happens inside GLNR. So what I meant is that GLNR is non-abelian. So exercise is to show that GLNR is non-abelian. Yeah, one can say that GLNR is a non-abelian group, but this is a standard practice to say that a group is abelian or non-abelian, just to simplify the writing probably. Okay, great. So you have met this notion of abelian groups and non-abelian groups, and you already know certain examples. And now your next task is to, determine the groups that you have met so far, to determine whether they are abelian or non-abelian. You have to determine whether each of them, to determine whether I mean, how many of them are abelian or how many of them are non-abelian. That will give you an idea. I mean that will allow you to somehow go through the notion of the definition of group once again to review what you have already learned, and that's a good exercise to work on. Okay, yeah, this is a very small exercise. Just takes a sentence, but I mean you need some time to spend on it. Okay, so here is another question for you. So, so could you write down the definition of non-abelian groups using, I mean, using this such an equation one, and just try to write it down. Okay. So here is this definition of non-abelian group. It says that a group is said to be non-abelian if it is not abelian. But again, one can try to write it in terms of an equation of this form. So please try to do it on your own. Okay. Yeah, and there are certain other terminologies which are also available in the literature, used extensively, which calls abelian groups as commutative groups, or sometimes non-abelian groups are called non-commutative groups. Okay, so if G star H is equal to H star G, then you say that G and H commute with each other. Okay, and yeah, if that happens for all GH, in other words, if any two elements of the group commute with each other, then yeah, so then the group is known to be commutative or abelian. And if that condition doesn't hold, then we say that the group is non-abelian or non-commutative. Okay. Yeah. So let's conclude this lecture here, and we will continue this notion of groups in the next lecture.